All right, so in this video, we're going to talk about, okay, in the previous video, we talked about applications of domain in calculation, where we treated several cases that are fractions, linear equations, natural logarithm, roots, and so on and so forth. Now, today we're going to talk about a subsection of that application of domain, which is the piecewise defined function. Now, the piecewise defined function is just it just gives you conditions. You understand? It's just like a function that has different conditions. A function that has multiple equations that each of the equation has a condition. You understand? Let me give you an instance. You can have a function f of x equal to, you have two equations, let's say x squared and x minus 2. This is a particular function that has two equations. Now, each of these equations will have a condition, x squared for x being greater than or equal to 1, or x minus 2 for x being less than 1. So if you have, let's say, they say if you find x is equal to 6, you're going to check, is x greater than or equal to 1, or is x less than 1? So if it's greater than or equal to 1, you're making use of this equation. But if it's the later, you're making use of this other equation. So let's tackle this equation now. This is a function, and let's say equation says find I f of 5 and I f of 1, I f of negative 3. And the first one, f of 5. So you're making use of, is 5 greater than or, you're going to check with the two conditions. So obviously 5 is greater than 1. So you're making use of the first formula. So this is going to be 5 squared because you're working with x squared, you understand? If f of x is x squared, that means f of 5 is 5 squared. You understand? So this gives you 25. Now for the second question, f of 1 means that x is 1. Now if f of x is equal to, now which of the formula we meant to use? You can't use the second one because 1 is not less than 1, you understand? Your x can be greater than or equal to. So x can be 1 or anything greater than 1. But x cannot be 1 here, you understand? X is less than 1. So you're still making use of the first equation. If f of x is x squared, that means f of 1 is going to be 1 squared, which gives you 1. Now for the third, I, if f of x is equal to, now negative 3 is obviously less than 1, so we're making use of the third formula, x minus 2, which is, now f of negative 3 will be negative 3 minus negative 2, negative 3 minus, okay, negative 3 minus 2, it gives you negative 5. So this is your answer. And this is just as simple as you can get, the piecewise defined function. Now let's take another question. This, if you have f of x being equal to 2x minus 3 and 5, and let's say for x being less than or equal to 1 and for x being greater than 1. Now let's say we are asked to find I f of 6 and I f of 0. Oh yeah, let's try to solve this. So solution for the first one, f of 6. Now 6 here is greater than, or is greater than 1, you understand? It satisfies this condition here. So for this kind of function, f of 6, there's no need to solve. What it means is that once x is greater than 1, the answer automatically is 5. You understand? There's no need to impute x. So even if you're asked to look for f of 10, the answer will still be 5. You understand? Because once it's greater than 1, your answer automatically is equal to 5. There's no need to solve because there's no x here. You understand? If there's an x, then you have to impute your value for x and solve. So the second question, f of 0. Now 0 is obviously less than 1. So we're gonna have to apply because there's x here. So you have 2 into 0 minus 3. This gives you 0 because 2 times 0 is 0 minus 3. Now f of 0 gives you negative 3. So this is basically what what piecewise defined function is all about. Now we go to applications of range in calculation. And we talked about domain and we talked about range. Now they're both similar. So what we do is that if you're given a function f of x as 1 minus 4x over 2x minus 1. Now if you are to look for the domain of this function, what you simply do is you just equate the denominator to 0, just like we discussed, and we know the reason why. Let's try that. So we have 2x minus 1 is equal to 0. 2x is equal to 1, because when this crosses over, it loses its negative sign. When you divide both sides by 2, you have x is equal to, okay, x is not equal to 0 here. X is not equal to 1 over 2. So in order to represent the domain for this, is going to be x, the domain contains a set of number x, such that x is an element of the real numbers and x is not equal to 1 over 2. And this is as simple as it can get. Now, this is for domain. If you're asked to find the range of this same equation, what you do first of all is you look for the inverse. You understand? When you get the inverse of this equation, then you just solve like you solved using the domain. You solve like you're looking for the domain. So now let's try that. Now, first things first, we have to look for the inverse. So the inverse, remember our step 1 is to make f of x equal to y. So y is equal to 1 minus 4x all over 2x minus 1. Our step 2 is to make x the subject, to cross multiply. Y multiplying 2x minus 1 equals 1 minus 4x. So we open the bracket, 2xy minus y is equal to 1 minus 4x. Collect like terms, so 2xy, this crossover becomes plus 4x equal to 1 remains where it is, and when negative y crosses over becomes positive y. So the reason why we brought all the x's together is because we want to make x the subject, so we can easily factorize. Now we factorize x is common, so x, what is left? 2y plus 4 is equal to 1 plus y. Now we divide both sides by 2y plus 4, so x becomes 1 plus y over 2y plus 4. Now our last step, our step 3 is to replace x with y and y with x. So y now is equal to 1 plus x over 2x plus 4. Just replace this. Anywhere you see x, you make it y. Now your final step, step 4, is to replace y with f inverse. So the inverse function of x is equal to 1 plus x over 2x plus 4. Now I've gotten the inverse of this function. Now the domain of this inverse gives the range of this, you understand? So now let's look for the domain of this. Now for the domain of this, same thing applies. This is a fraction, so the denominator cannot be equal to 0. So 2x plus 4 cannot be equal to 0. Take this over to the other side. So 2x cannot be equal to negative 4. Divide both side by 2. You have x cannot be equal to negative 4 over 2. X cannot be equal to negative 2. Because when this divides, you get negative 2. So to represent this in our set builder form, we have x can be set of numbers such that x is an element of real numbers. Then the exception is that x cannot be equal to 2. Understand? So now this is the domain of this inverse, but in the close-up, we are asked to look for the range of this, right? So the range of this is equal to this. So this is the range of this function, understand? The domain of an inverse function is the range of the original function, understand? So this is just the step. Step 1, you find the inverse of the function. Step 2, you look for the domain of that inverse function and you have your range. Now another way of representing this is your interval notation, and you have this as negative infinity, comma, negative 2 union, negative 2, comma, infinity. Infinity. So we'll take another example for more clarity. Now let's take another example. Okay, number 2. Now f of x is equal to x squared plus 3. Now we're asked to find both the domain and the range. The domain of this already, just this, is a linear function. So the domain is all sets of what? Real numbers. Or you can put it this way, negative infinity, infinity. That is for the domain. Now the range, if you're asked to look for the range of this same equation, what do? The first thing we have to do is to convert this to an inverse function. So what will it look like? So we have y will be equal to x squared plus 3. You make x the subject. So x squared plus 3 gives you y. Just exchange the position. Now when this crosses over, it becomes x squared is equal to y minus 3. Now x becomes the square root of y minus 3. Just another step, interchange x for y and y for x. So y becomes the square root of x minus 3. Replace y with the inverse function. So inverse function of x gives you the square root of x minus 3. So we're meant to look for the domain of this. Now remember, this is a square root. The domain of a square root, what is inside must be, for a square root, what inside must be greater than or equal to 0. That's the condition. So x minus 3 must be greater than or equal to 0. And when this crosses over, x must be greater than or equal to 3. Now what does this mean? On the number line, you can have 0, 1, 2, 3, 4, down to what? Infinity. Now x can be equal to or greater than 3. So the set of values can be either 3, 4, 5, 6, down to infinity. So in order to represent this in interval notation, we can use a bracket. So to show that 3 is among, and then use a parenthesis for the infinity sign. So this is 3 and infinity. You can also denote these two things in terms of set builder forms. So just a personal choice. So these are the domain and range. This is the domain and range of this particular question. And finally, can have a question like this. Find the domain and range of this. Now, the cube root of x minus 2. Now, when we talked about square roots, we said something. we gave a condition for square root. We said the contents inside the square root must be greater than or equal to 0. But now, for a cube root, and we gave reasons why, because you cannot have square root of -4. For you to have this means that -4 must be a perfect square. Means that a number must multiply itself twice. What do I mean? If you have the square root of 16, it means the square root of 4 times 4, which gives you 4, right? Now, -4 is not a perfect square. 4 is a perfect square because you have 2 times 2. 16 is a perfect square because you have 4 times 4. But -4 is not a perfect square because when you multiply 2 times 2, you can't get -4. When you multiply -2 times -2, you can't get -4. It's going to give you +4. So this is not a perfect square. Now, this is for square roots. But for cube roots, let's take an instance. Let's say, we have perfect cubes, right? Now let's say 8. 8 is a perfect cube. Why? Because you have 2 times 2 times 2. -8 is a perfect cube because you can have -2 times -2 times -2. This will give you +4. +4 times -2 gives you -8. So you see that inside a cube root, you can have a negative sign. Now the trick here is that if it's a square root, a square root is just like this. If it's a cube root, a fourth root, a fifth root. Now the trick is for the even roots, that is square root, fourth root, sixth root, negative signs are not allowed inside. But for odd roots, negative signs are allowed inside, you understand? So this can permit negative inside of it. This can permit negative inside of it. So now we try to solve this question. This is a function f of x is equal to the cube root of x minus 2. So what is the domain and what is the range of this question? Now for the domain, since there is no condition, anything can work inside of this, you understand? Any number, because you can have a positive answer inside of it. So the domain is just a set of all real numbers. So let's use set builder notation for this. So you have x such that x is an element of real numbers, and that's all. Now for the domain, you apply the same principle, y being equal to the cube root of x minus 2. You find the cube of both sides, so y cubed becomes x minus 2. You make x the subject, x minus 2 becomes y cubed. X gives you y cubed plus 2. Replace x for y and y for x. So we have y is equal to x cubed plus 2. Replace y for inverse. So f inverse gives you x cubed plus 2. Now, the range of this, the domain of this gives you the range of the original equation. So this is a linear function. So the range of this equation is the domain of this. So the domain of this, since it's a linear function, is still all real numbers because there's no condition. So this is basically the range and domain of this particular equation. So I think this is the end of this video, introductory part to mapping and function. Thanks for watching.